today we have Professor Hong Yim here to give us a talk. So I will start with a brief introduction about Professor Yim. He received his bachelor's and master's degree from Seoul National University, and the PhD is from Princeton University. After postdoc researcher appointments at the Center for Turbulence Research at Stanford University, and then at the Combustion Research Facility, Sandia National Laboratory, he held assistant, associate, and then full professor positions at the University of Michigan. He then joined KAUST in 2013 as a professor of mechanical engineering. He is a recipient of the NSF Career Award and the SAE Lawfield Teacher Educational Award, and has been inducted as an international member of the National Academy of Engineering of Korea, a fellow of the Combustion Institute, and ASME and AIAA. He has also served as an associate editor for the Proceedings of the Combustion Institute, and currently on the editorial board for Energy and AI. Professor Yim's research and teaching interests are primarily fundamental and practical aspects of combustion and power generation devices using high-fidelity computational modeling. Current research activities include direct numerical simulation of turbulent combustion at extreme conditions, large simulations of turbulent flames at high pressure, combustion of hydrogen and e-fuels, supply and combustion modeling in advanced internal combustion engines, advanced models for pollutant formation and plasma-assisted combustion. So he's going to give us a talk today about high-fidelity simulations of hydrogen and ammonia turbulent premixed flames, physical characteristics and modeling implications. So before I hand the floor to Professor Yim, I would like to remind all the audience here, it's good to see that we have 80 now, that during the talk, you can raise your questions. You can use the chat function at the bottom of the screen, type into your questions there, and then at the end of the talk, I will ask the questions on behalf. So I think we are ready here. So I will hand the floor to you, Professor Yim.
Thank you. All right. Thank you very much for a very nice introduction. Good morning, good afternoon, good evening, good night, everyone all over the world. It is my great pleasure and honor to be able to speak in this the honorary lecture series. It's my great pleasure. All right, so today I will talk about what is hydrogen ammonia combustion as title, but there are a lot of things going on in my group. For the general, I understand this is a fairly well-educated combustion audience, but still, just for the targeting for the general audience coming from fundamental to applied field, I don't intend to go into too much in-depth analysis and theoretical aspects, but just to kind of briefly touch on the subject of high-level science questions, and followed by some modeling aspect, computational aspects of the DNS, and that's a general story today. So before I start, let me introduce all my great colleagues at CCRC. As many of you probably recognize very well. Bill Roberts is a director, and we have a total of currently 10 active faculty members associated with the CCRC. Well, unfortunately, I am currently the only computational modeling person that keeps me very busy, collaborating with many other brilliant experimental people. We have some new addition of Jamie Turner on IC engines. Bassam Dali recently joined as well, and he's working on branching out into some other aspects. And we have also Shu Lu, he's working on some fuel cell and the other catalytic aspects of the hydrogen production. So our focus and interest is also expanding. So I would like to give a few minutes. I understand many of you already know about CCRC KAUST a fair amount, but I'll give you a brief overview of it, only for a couple of slides. It's a big group. I guess CCRC by now has grown into one of the largest combustion research institutions. We have nearly like 200 people altogether, including PhD students and postdoc research scientists, and altogether. We have produced over 150 alumni, and they are really doing well in their professional career. Well, so our 10 faculty members are covering all sorts about combustion research. This is what I kind of created as a regime diagram of a CCRC. We cover all the physical scale, and also we complement each other between modeling and experiment as well. So starting from chemical kinetics to flame DNS, that goes into large eddy simulation, and then device level IC engines. So these are kind of our premise. We kind of cover everything there is about combustion, reacting flows. We can cover that. So let me switch to my group. My group has grown quite a bit. Also, I have total 26 members in my group at the moment, with many outstanding postdoc students and altogether. Those who directly contributed to today's presentation have been highlighted in red colors. So Francisco, Minbao, and Harsha, Ruslan, and Wanshik, and those are the main contributors in the DNS area. So as I told you, I cover all sorts of experimental work, and by doing so, I do all three classes of the simulation, starting from DNS, which has been my kind of primary activities before when I was at Michigan, but I branched out a lot more into LES for the device level flame simulations, and the IC engines. We have been closely working with Saudi Aramco on future engines. So it's a little too much to cover. So today I'm going to only pick one of the three topics, which is about DNS. And specifically among the DNS, we will talk about this as classical box, flame in the box kind of configuration. All right, what's the frame? Again, well, I guess this is becoming kind of cliche in today's combustion talks. So I'm not gonna, again, spend too much time on it anymore. The Saudi government is moving forward into this so-called circular carbon economy. So we want to achieve this sustainable ecosystem where we don't produce any carbon, so that we can either use a current hydrocarbon or even future e-fuels altogether. So there are 4 R activities under CCE: recycle, reuse, and remove, and reduce. And you can see there are a lot of things that our combustion community can contribute. So again, to the general audience, I guess we all agree that combustion is still has a vital role toward the sustainable future, especially in the context of the solar fuel. So if you assume that solar energy is going to be the main source of energy in the future, so-called power to X is the ultimate viable solution. And the X can be electricity directly into stored batteries, but we believe there's a lot of existing infrastructure and also storage and transportation. These gaseous and liquid fuels, the synthesis of those will really provide a significant role in making everything work in an integrated way. So with that, everyone knows, and we are going full blown into hydrogen, which is one of the basic e-fuels. And one next step, since hydrogen is difficult to carry around, so ammonia is another one that is gaining a lot of research interest. So those are kind of basic framework where we're gonna talk about. And like I said before, CCRC, we've been firmly based on fundamental chemical reactions and flame studies, but we are slowly branching out into, of course, the e-fuels, but on top of that, the carbon capture aspects And concentrated solar power is another area that we're expanding into with the Bassam Dali. As I also said, we also have a hybridization in transportation as well as a fuel cell activities are growing. So we are also diversifying into more comprehensive energy research institution. So I talked about hydrogen and ammonia as one of the major e-fuels for the future. I think it is very important to develop combustion technology of that, how we can burn them cleanly and efficiently. Well, the chemistry for hydrogen and ammonia, hydrogen is fairly well understood. Ammonia, not as much so, but still both are fairly simple fuel. So their chemical pathways are relatively simpler compared to other engine fuels, but burning them really cleanly and again, efficiently requires a lot of fundamental knowledge. So there's plenty of work to be done. And just to, I guess everyone knows this, but one of the three, I would name three key questions about making it work. Those are, in the case of ammonia, it's just really difficult to burn. So how can you make it burn faster? In the case of hydrogen, it's burning a little too fast. And there's a problem of flashback issues, and those are another fundamental issues to deal with. And both of these scenarios, well, if you kind of burn it at high temperature, the NOx formation is going to be continuing issues. So those are the three issues, especially for ammonia, that we need to resolve. Well, just as a disclaimer, I'm not going to talk any of these today in my presentation. This is still a work in progress, and along with many other community members, but I am trying to contribute to this knowledge development by utilizing DNS as a research tool. So DNS, well, everyone knows about what it is. It is essentially I guess we have to be careful about the terminology. The word direct actually came from the turbulence community, the non-reacting flow, in a way that we are using full Navier-Stokes equation without closure models. Well, in the case of reacting flows, actually the Arrhenius reaction rate expression itself is a model, unless we go into the molecular kinetic scale. So in a way, direct numeric DNS is a misnomer, but that is the context. So by that, what we mean is that we are solving for all the continuum scale without any turbulent closure model, although reaction, we accept that it is still a kind of curve fit model based on Arrhenius form. And the role of this DNS is that by resolving everything in the most accurate temporal and spatial resolution, we can understand the science, physics about turbulence flame interaction, and those knowledge can be used in developing advanced submodels for high fidelity engineering simulations. So that's the context. So what I'm going to talk about for the next maybe 35 minutes is three parts. I will show you some, I've done this flame in the box for hydrogen flames for a while, for some time. Actually, 10 years ago, I was starting with a hydrogen flame and hoping to, well, once I get enough about hydrogen done, and I was hoping to move into hydrocarbon flame, which is a real thing. While I was getting ready for doing that, now nobody's interested in hydrocarbon anymore. Everybody's working on hydrogen. So, well, I just stayed away on the same path as it is now, except I'm going to add on ammonia flames. I must also say that ammonia flame simulation has been recently started. So this is going to be only a brief report of the work in progress. And I will also, followed by that, I will briefly give you how these DNS data can be used in model validation. And that I'll only give you one example. I work with many other colleagues on the providing this data for model validation, but this will be just one example, collaboration with the University of Toronto group, Sweta Provo Chaudhuri. And I will try to leave enough time for the last item, because this is a fashionable item, I guess. everyone wants to use AI machine learning. And my current focus in utilizing machine learning technique is how I can utilize it as a way to accelerate this DNS simulation, which is very time consuming. So I will give you a couple of those examples on my recent effort. So that's the outline. So let's get started. So the hydrogen air premixed flame in a box is a main theme. You will repeatedly see this flame in the box over and over. I will just give not the gory details of what we've done in the series of papers, but I will just highlight the key messages for the general audience. We start with the atmospheric, and then more current interest is elevated pressure conditions. So we have also conducted that as well. So I'll give you some extra insights into that. So this is a kind of a YZ direction is a periodic box. We provide the turbulence, homogeneous isotropic turbulence generated from spectrum function. You feed it in. And we recently started working on turbulence forcing scheme. And so this turbulence is maintained all the way just before it hits the flame. There is a long debate as to how we should maintain the turbulence strength, and but I'm not going to get in there. Our approach is that we filter it out so that it just stops before we hit the flame edge. Otherwise, the forcing turbulence in the middle of the flame may lead to unphysical behavior. This is the compressible reacting flow DNS code, is similar algorithm as Sandia's S3D, but I have implemented into the new framework, which is named as a KAUST code. Again, the basic algorithm is the same, but the main thing about this KAUST is I called it adaptive in a way that it is adaptive in CPU, GPU hybrid architecture. So I'll get to that point later on. The mechanism is well known, so we use the latest Princeton mechanism with the 9 species and 23 reaction steps. So well-known regime diagram, Borghi diagram is here. So, well, just in case those who are not fully familiar with Borghi diagram, the vertical axis indicates the turbulence intensity, U prime, normalized by flame speed. So and then the right x-axis is a length scale ratio between integral eddies relative to the flame thickness. So Reynolds isoline, Reynolds number in the metric of the turbulence intensity gets higher and higher as you move to the upper right corner. And at the same time, Damkala number, which is the metric for chemical intensity, becomes stronger and stronger chemical reaction as you move to the lower right. And in the meantime, the Karlovitz number, which I don't like personally, the Borghi diagram. I had a chance to speak about it in the past, but Karlovitz number is actually kind of inverse of Damkala number, except the length scale is coming from the Kolmogorov eddies instead of an integral eddy. So large Karlovitz number roughly corresponds to low Damkala number. And this is something I never liked. And I like the Foreman-Williams version of the regime diagram, but I'm just a minority. Anyway, this is commonly adapted. So we picked the first 4 parallelogram as a hope that we will maintain Reynolds number in 2 cases each, as well as a Karlovitz number axis. Because many people have been arguing about the importance of Karlovitz number because the Williams, Klimov-Williams criteria requires that if the Karlovitz number gets bigger than 1, Kolmogorov eddies interfere into the flame, the whole dynamics change and blah, blah. So there has been a lot of efforts in the experimental group as well to push the turbulence level higher and higher until we realize this kind of thin reaction zone and broken reaction zone regime to understand the totally distinct fundamental characteristics. So that was the intention. And then later on, for the reason I'm going to elaborate a little bit later, we added a few more points. And as you may see, those are 3 and 5, case 3 and 5 are vertically aligned with the F2 matching LT over delta L. And there's a reason for it, because as we found out, it is not Karlovitz number, but actually it is LT over delta. That scale is actually pretty much all that matters. So all the rest of these parametric conditions are given here. And we also have added F3 and F4 just to fill the gap in between. But I will kind of occasionally show as needed all those results. Well, picture tells 1,000 words and movie tells even 10,000 words. So you can appreciate the flame structure, how they change as the Reynolds and Karlovitz number changes. So these are 1, 2, 3, 4. Let me remind you, 1, 2, 3, 4 corresponds to parallelogram. So 2 and 3 are on the vertically the same axis. And F1 and 2 share the same Reynolds number. 3 and 4 share the same Reynolds number. 1 and 3 and 2 and 4 have the same Karlovitz number. So what would you pick as a similarity between the two? Well, I guess the case F1 is a further out into this L over delta ratio, and as meaning that you have a much larger integral eddy scale that has enough power to disrupt this flame front. So you can clearly visually see the flame structure is a lot more wrinkled compared to the others. And 2 and 3 are compared, despite the fact that Karlovitz number is orders of magnitude difference, they are visually not that much different. In terms of, by that I mean small scale features are here for sure, but the front to back, the thickness of the turbulent flame brush are not that different. And furthermore, 2 and 4, they are at the same Karlovitz number, but as I bring it down into the small Reynolds number, well, you hardly don't see a whole lot of wrinkles at all. So that is a kind of visual observation. So we conducted, how does that affect the overall turbulent burning velocity? Of course, this turbulent burning velocity correlation effects of turbulence on overall flame brush speed has also been beaten to death for many decades. Still, we are not clearly sure exactly how we should scale them. So we conducted the overall consumption speed analysis, which is a true metric of the flame speed, and then also displacement speed just to measure the local front propagation speed in a density weighted manner. Here's a result. So once again, just for the reference, I give you the Borg diagram on the right to appreciate the difference. So as I said before, the black is the overall burning rate, red is the area enhancement, and they all align pretty well. So that's the first thing to observe. Well, so all range of Karlovitz, Reynolds, all that conditions, burning rate enhancement is pretty much dictated by the surface generation, even if the Karlovitz number was like 1100. And which one has the highest burning rate? As you may recall, the very first one showing the lot of corrugation has the largest flame enhancement, speed enhancement, while F2 and F4 prime, which is around here because F4 was a little too small. So both of those cases, Karlovitz number is the largest, but they barely do anything about enhancing the flame speed, other than just barely a factor of 2. And F3 and 5 are somewhere in between, but still F2 and 3 being on the same level, although F3, which has the larger level of wrinkles, but their overall enhancement seems to be comparable. So basically, this is called the Damkala's first hypothesis, as you can see Peter's textbook. Even all turbulent Karlovitz number ranges, the dictating factor of the burning rate enhancement is ST over SL. And that ST, the area ratio that is, and that is mainly dictated by the integral scale eddies. So even now, if there's any one take-home message for the audience today, that statement is that over and over through the many simulations I found out, the Karlovitz number effect is overrated. That's my opinion. And I'm sure some people might argue otherwise. And they argue also, some counter argument is that this turbulence is by definition decaying as the turbulence passes through the flame, and which is exactly the reason why this is observed. But well, I would argue that what are the situations that it doesn't happen? So I think this flame in the box configuration still represents fairly practically relevant scenario of a turbulence flame interaction. And this is a key message here. And those have been further demonstrated. Each of these dots represents the black dots, for that matter, are the 7, 8 different cases scaled up here. And you see the cluttering of these 3 points, which are totally different Karlovitz number, but they overall align on the same spot. And when you want to enhance it more, this is F1 and so on. And this is mainly the scaling with the LT over delta L, which kind of it's not the first time we report this. It is literally the Reynolds number effect that many people in the past hypothesize is Reynolds number scaling. So that's the first message I would like to convey today to the audience. And the detailed flame, in order to understand the flame structure at different Karlovitz number conditions, we have done the PDF of the local flame speed. That way we understand how we are close to the original wrinkled laminar flame net idea. And surprisingly, again, for all these different conditions, they all look similar with the PDF peak nearly the same as a laminar flame. The dotted line is a laminar flame result, and they are not deviating too much. So in other words, the statistical average of the flame structure, as you can see here, they all look similar to laminar. They're not far off. Here again, dotted lines show all the baseline laminar flame profile as a function of progress variable based on temperature. And the solid line is a turbulent statistical average of the turbulent results for my different cases, with the shaded area as a variation. Then, so the solid and dotted curve, they all pretty much align and not that far off. So average profile resemble 1D laminar flame. Even Karlovitz number is 1100. So all these are broken zone and the distributed combustion regime may not exist. And I believe that many of the turbulent experiment data also supports that conclusion. So I think that's the kind of a key message here. If anything, some deviations are happening with the intermediate species, but again, it is the level of the discrepancies between laminar and the turbulent cases are the largest in the order of LT over del, as I mentioned earlier. So F1 shows the largest deviation and so on. And then as you go to the left of this map, F2 and 3 shows the next largest deviation. F4 prime and 5 shows smaller. In all cases, it's remarkable to find the largest deviation from laminar flame happens at far upstream, which is attributed to the fact that I have more intense turbulent eddies further upstream of the flame zone. And that has actually further impact in the high pressure combustion mode, as I will show in a moment. So now we are moving on to pressure now. So that was a simple key messages. And we have also having understood that is moving along the horizontal axis matters the most in terms of affecting turbulent burning velocity. We did the pressure effect, and you can change the pressure in different. You can change it in different ways. We can elevate the pressure, and while so P1357, which is shown on the lower, we maintain same U prime. But since you pressurize it, flame thickness gets smaller. So if you maintain the same physical integral eddy size, then the LT over delta L increases. So that's why you automatically naturally move to the right. Alternatively, we have also run the cases staying in the same point by reducing LT along with the flame thickness so that we maintain the ratio. So that we will kind of highlight the difference between the two scenarios. And here's again the animation images of as we move to the right. Again, without no surprise, as you move further into the larger LT over del ratio, you find much bigger wrinkles, and that is going to contribute to more enhanced burning rate. And so these are the general same plot of the STSL enhancement as a function of over time for different cases. Just again, the Borg diagram is shown here as a reference. So the lower row is the moving to the right. And as you can expect, the flame speed enhancements gets larger and larger from 1357. Although if I'm sitting on here, like I told you, the enhancement hardly changes, although there's a final push above as you push the pressure up to 7 bar. And another thing to observe is that there are a little bit more spiky behavior observed here. And those are the two key observations. So once again, the point that LT over del has a dominant factor in terms of burning rate enhancement is further supported even at high pressure condition. That's one maybe not a breakthrough, but some meaningful finding. Speaking of the spiky behavior on P7, we attribute that to the shift of the curvature statistics. And this is a curvature statistics, and the mean value of the curvature is tilting toward the positive line, especially when you are dealing with P7 prime, which was shown here. So the spiky behavior in this sudden burst is attributed to this pointy leading point of the turbulent flames. So there are some people arguing this leading point concept is dictating this flame propagation behavior, which is still controversial. Okay, speaking of the burning rate enhancement, once again, as we move to the right, the enhancement is bigger. That's a black curve. Red is area ratio. Again, they are correlated, although there's a little bit bigger gap as you increase the pressure. And this dotted line is staying on the same LT over del. So they remain all the same except for the little push, as I told you earlier. So these remaining discrepancy and the additional push is attributed to the combination of reaction and diffusion. What do I mean by that? Well, the additional chemical boost, as we found out, was that we observed the flame profile of the reaction, the heat release rate profile across the progress variable space. And the blue are both the high pressure condition. As we zoom in, we find out there's quite a bit of enhanced boosted heat release rate far upstream near a CT of less than 0.1, which what is the temperature there is nearly barely 400-500 K. So what's going on there? I mean, what kind of heat release mechanism is out there? Well, I guess if you know well enough about basic hydrogen chemistry, you know what is the main contributor to heat release, which is H plus O2 recombination reaction. And without surprise, that is actually the main cause of that. And as we know, even the regular atmospheric hydrogen flame, this one contributes a lot, and this one peaks way up in front. And this is what makes a hydrogen flame rather unique compared to many other hydrocarbon, where heat release is occurring way ahead in the preheat zone. And this is even more so, as we find out, as you increase pressure to 7 atm. And how is it happening? And this is augmented by, as we found out, by the transport of hydrogen way out into the upstream zone. So diffusivity is reduced, as you may know, at higher pressure, but at the same time, gradients get steeper. So all the net effect is that these high pressure conditions, you will have more effective transport, the diffusive transport of H2 into farther upstream. So as a result, you will see a lot more larger level of heat release rate and even more than linear scaling. And that's what we found. And this is additional effect attributed to the enhanced burning rate. Okay, I think I'm doing fairly well in time management. So those are the kind of a gist of, there are many other gory details of analysis and interpretation, but these are the key messages I would like to convey today. And this DNS data is quite expensive. Each run takes up a few million hours easily, sometimes even up to 10 million CPU hours. So they are precious, and I've been working closely with many other colleagues to provide this data for the validating some theoretical model. So some of the recent work that I collaborated with the Sweta Provo Chaudhuri at the University of Toronto is about the upstream flame interaction model. So as we have more and more corrugated turbulence, so well, step back a little bit for a moment. Well, we all know, I guess most of people in this audience are familiar with this stretch model dating from 80s about linear relation of Markstein-Karlovitz number. And that has been further extended because this is linear relation doesn't hold too well if the curvature becomes very large. So there has been an attempt to separate out stretch Markstein number and curvature Markstein number separately. And that is more in the 90s and 2000s. And that seems to match the data better. Now, if you go into even further into the bigger, larger level of curvature, what happens? Well, then you need to start worrying about flame upstream interaction and annihilation. And this is what the Chaudhuri group has been doing. And they, with the Dave, and this is not me, but Dave and Chaudhuri, some years ago, they developed this very nice, elegant theoretical model based on scaling analysis, how we can modify the displacement speed of the flame front as a function of curvature with the extra correlation coefficient. That effective coefficient is a function of representing these flame interaction behavior. And that model was validated again against the DNS study, but their data was fairly low Karlovitz number. So does it extend to high Karlovitz numbers condition? And that was our question to answer. And well, like I said earlier, well, Karlovitz number is overrated. And our conclusion was, yes, it does work. So here is just a brief synopsis of the result. We try to correlate out of these 4 different cases, 1, 2, 3, 4, those correspond to the same cases at atmospheric conditions, as you find. So some of the Karlovitz number range goes above 1,000. It's a forced turbulence, it's real, but nevertheless, their theoretical model, which is shown as a dotted curve, dash curve, fits very well. So let me step back. We did the analysis for different isosurfaces, 385, 641, and 4 different levels, so way up in the upstream preheat zone, all the way down to the downstream region. And as you can see here, when you are capturing the flames, the displacement speed of the downstream region, the model based on original, the models, the solid line without this flame interaction tends to work better, because this dashed dot blue line is the actual curve fit based on DNS data. And you can see the black solid line aligns better with that. On the other hand, as you move up into the upstream, actually the new model based on accounting for the flame interaction aligns better there. So what's the message? I guess the implication is fairly clear. Here's a picture sketch of that. So so as Kaulov's number gets higher and higher, this is a kind of a, well, so this is my interpretation and my picture of high Kaulov's number flame structure. Basically, you get a lot of more wrinkles in the isosurfaces, but it decays down by the time you get into the downstream of the flame. So it is no wonder that as you are further into this isosurface, 385 or even 641, they are a lot more corrugated. So obviously the flame-flame interaction behavior is going to be more prominent, and which explains why they align better with the high Kaulov's number. And it is remarkable to see that the agreement is a little bit off, but if especially at high Kaulov's number condition, what was that? Well, they align well, but deviation level is still reasonable, and they seem to predict the behavior fairly consistently. So that was one kind of quick example of how we apply this into the model validation. Okay. Well, ammonia flame, I don't have much time to right now, but again, this is work in progress. So what are the distinct point of ammonia air, the premixed flame? So, well, I think I can nearly skip this. Well, everyone knows what's issues of ammonia in practical application. I would like to understand the fundamental characteristics of turbulence flame interaction in ammonia flame. For one thing, ammonia flame, if it's a neat ammonia, the heat release rate profile is switched further into the backside of the downstream side of the flame. So we are still in the process of investigating it, but my expectation is that in the context of this turbulence, homogeneous turbulence decaying across a flame thickness, I think the characteristics will be quite different. So we tried the low and high LT over delta L, following similar to the hydrogen counterpart, and we ran 5 cases. And there's one more A1 prime case, which is we picked the 1.2 equivalence ratio, which was found to be the peak, the flame speed. And then I picked another lean condition, slightly lean condition, but to compensate for the lower flame speed, to match the net laminar flame speed here, we had to preheat the upstream a little bit more. And so we compare the burning rate behavior. So once again, 3, 4, 5 are higher LT over del. So that behavior doesn't change. We see a lot more flame wrinkles, and therefore flame speed enhancement is observed. A1 prime is supposed to be compared with against A1. Those are comparable LT over SL, LT over L, well, LT over del, and similar turbulence intensity. And so we want to see how they fare in terms of flame burning rate enhancement. So here are the comparisons. So let me first focus on A3, 4, 5. In the interest of time, I'll keep it short. One interesting finding here was that, which I don't have clear answer yet, is that there is non-monotonic flame speed enhancement as you increase the LT over del from the A3 to, no, A3 is right here actually, and A4 and A5. And there's a kind of, the burning rate enhancement goes up and down. That's one. And comparing A1 and A1 prime, those are comparable condition, but A1 prime, the lean condition, at the comparable Kaulovitz and Reynolds and everything, U prime over SL, delta, LT over del, all the same, but it shows a little bit more enhancement. And that behavior, it turned out, is found to be the effect of Lewis number. So again, Lewis number has been investigated extensively. Here is again playing the role even in ammonia flame. So the lean ammonia flame, as you can imagine, this got the effective Lewis number is less, and that difference of effective Lewis number makes up for that much of the stretch factor difference. So that is a tentative finding, although ammonia flame produces a lot of hydrogen as an intermediate species, and how that plays a role in the context of this Lewis number effect is still quite complicated, and that needs a further work. Okay, let me spend, hopefully, can I spend, how are you doing in time? We have 10 more minutes, is that okay? Maybe 7 minutes, all right? I'll finish up with the different context of computational aspects. Now, all these DNS simulation, if you want to ramp up the scale of simulation, it becomes very expensive. So there's a constant need, no matter how the computational hardware becomes faster and faster, still we want to do more and more. We want to run faster and faster to achieve a big simulation possible. So I've been working, I had a pleasure of working with the two brilliant colleagues, one Professor Mauro Valorani at the University of Rome and Venkat Raman at the University of Michigan, and two different aspects of how we can further accelerate these DNS simulation. So that's, I'm gonna just quickly give you a glimpse of the gist of the concept. The first is acceleration by theory, by utilizing different time scales. So using computational singular perturbation. So I have worked with the Mauro Valorani for many years, more than 10 years on this CSP analysis. So what CSP is essential, it's a fairly simple automated eigenvalue decomposition. So if I have any reacting system of the n scalar species, for example, and then there's n orthogonal, if you convert them, transform them into the eigenspace, you can find n eigenvalues representing different distinct time scale of these characteristic chemical modes. And you can rank them in the order of from fast to slow. And oftentimes there's one big gap in between. So the whatever is smaller than that short time scale is called fast, exhausted mode. And those are usually reaching steady state. So we are not really interested in capturing that dynamics of that fast time scale, but those fast time scales are the ones that is putting a lot of computational burden. And what we are interested in is capturing all these slow mode, and that is actually driving the dynamics such as ignition or flame quenching and so on. So is there any way we can systematically separate them out and set these fast time scale into the exhausted mode? And that's what we are doing here. So this CSP application allows us to reduce the timescale stiffness by only downsampling the slow modes, while fast modes are reaching these quasi-steady state. And this quasi-steady state can be guaranteed by this projection approach. So we call it the fast subspace, slow subspace. This fast subspace is reaching equilibrium, steady state. And that operation is called the radical correction. And you kind of basically, it's like a projection technique in incompressible flow solution solver. So once you march it with the slow mode and then project it to make sure that this steady state is exhaust mode is established. So the algorithm is the following. For starting from any current type, you first do the radical correction just to make sure your fast scales are exhausted, and you do the explicit time integration. Here's another important thing. You don't want to necessarily use implicit time integration, which is costly. So now that all the fast time scale is eliminated, the easiest straightforward way of doing that fast integration is the explicit scheme. So you go quickly to next time step. Now you deviate from this manifold and you apply the second radical correction to stay back on the track. So these are the general algorithm, which works out very well. One key drawback, this has been around for some time, but one key drawback of this method is that in order to apply this as CSP and radical correction, we need to compute the CSP basis vector, which is the basically linear algebra eigenvalue determination. That is quite expensive. So our idea is, this is a general approach in the numerical algorithm, as I just described. So now our idea is that speed things up by replacing this basis vector evaluation by using machine learning, using the artificial neural network algorithm to fast compute this based on that database. So that was the gist of it. And so we have reconstruct this projection basis based on ANN algorithm that speed things up significantly. And the thing is that, since one important thing to note, without getting into too much detail, the errors in this basis vector, the estimation using ANN does not affect the solution accuracy. That is a very important thing. So unlike many other application of ANN reacting source term react evaluation, where those ANN error directly translate to the solution fidelity, here it is not. It only affects the ANN reconstruction part. So that's another important advantage of this approach. So quick demonstration has been done, which was published recently in JCP. So we were able to capture the ignition behavior almost accurately, while the time step following the CSP solver as well as CSP ANN. CSP solver means I don't do ANN in determining eigenbasis. So they will yield nearly the same delta t, which is orders of magnitude bigger. And ANN solver will be much faster because that the basis vector evaluation is much faster. Okay. So one last thing. So another aspects of speeding things up is the hardware aspects, CPU, GPU. So GPU is quite a significant portion of the supercomputer today. So we want to take the advantage of it. So, well, as many of you already know, what GPU does much better than CPU in reacting flow simulation is a reaction source term evaluation, because those are usually the local computation and a lot of number crunching in a local space. So it is really well suited for GPU. So trivial is a GPU solver as opposed to a conventional CPU based, like for example Cantera, Chemkin. The GPU based reaction source term evaluation is matrix based, right? So to take a long mathematical theory short, it is basically you have a matrix and then you just operate it at one shot. So that's been done, and especially Michigan team has developed the Michigan Chem GPU algorithm. So basically what it does is again, as I said here, it's a CPU based evaluation. You do it sequentially, but GPU based is a matrix based. So the bigger your domain, the computational cells, you just operate it all at once, so it can speed things up by orders of magnitude. Well, it all sounds good. So now the question is, can we really speed things up a lot into actual CPU GPU hybrid system? So we went ahead and tried to do this, apply this. Well, so I'll skip that. So so you can imagine, compared to Chem GPU, which is a GPU solver developed by Venkat Raman group, compared to Cantera case, as the grid block size increase, obviously speed up gets enormous, over thousands of fold. So do we expect that much of the scale up of the acceleration? Well, unfortunately, when you try to combine CPU solver, like any typical CFD solvers, this is the chemistry speed up, as we have seen, but the net code overall speed up is not that impressive. It barely goes up. So when we first found that out, it was just shocked. What the heck is going on? And as it turns out, the answer turned out to be fairly simple. It was mainly attributed to the data copy. So I think I'm running out of time, so I'll just speed up. So it was basically CPU, GPU not only switch the information, but also it has to copy a lot of this information. And this memory copy costs a lot. And that is actually bogged down to all the bottleneck of the speed up. So one nice thing about my code curves is that we can compile the whole MPI code with CUDA so that we don't have to do so many data copy. It's not required. So there was one advantage of utilizing KAUST. So we did that, and we were able to achieve much faster for various types of NVIDIA GPU card. We were able to achieve expected level of speed up. And so that was quite an impressive, but I think, well, it is more like some obvious finding after the fact, but it was quite a mysterious for a while. So I thought it's good to report to the community where there are many people working on this kind of GPU acceleration. This is one interesting information to be reported. And one last, yeah, so this is called the well-established graphics of the roofline model, which we learned from other computational group of people. So, well, roofline model the curve is very simple. So x-axis means the arithmetic intensity as you on the GPU. So as your algorithm becomes more complicated, you have to compute like a diffusion and whole bunch of reactions per node per each cell. You will reach that region. And then at some point, each of the GPU card will have a performance limit. So the flops per second is a performance maximum. So you want to, but before you hit that, basically, unless you saturate your GPU with the arithmetic intensity, you are memory bound. And this is what I was telling you about earlier, that the memory copy interaction across the CPU, GPU was slowing down. So the chart actually, as you map it onto this chart, you get a clear idea of where you are at. And the idea about this GPU allocation is that you want to be beyond this bandwidth limited region, and you want to reach around here. You don't want to go that further away here. You may need to break it down here because you're not going to improve the performance down here. So that is an optimal level of arithmetic intensity you want to allocate. So we took our test case scenario into this, and we can exactly see where we were in those test runs. And again, without surprise, you can see that as we increase the number of cells, increasing the intensity, you are reaching up to here. But when you are down here, you are still memory bound. So you want to push it up to reach the maximum performance. So I think we are learning as we go. And this is not a kind of conventional combustion research, but I thought this could be a useful information for the community. So I think time's up. So with that, I'll just quickly summarize. I'm not going to even read this. I would like to make 3 bullet point items. Combustion still remains relevant, and hydrogen and ammonia combustion still needs a lot of studies. And exascale computing brings up a lot of additional research opportunities to improve the application of machine learning so that we can reach high speed and large scale simulation. Thank you very much. I'll be happy to answer any questions you might have.
Thank you very much, Professor Yu, and for this very inspiring talk with a lot of information. We do have a couple of questions in the chat. So I will ask on behalf of the audience. The first one is from Professor Jay Guo, I think. The diffusive transport increases in spite of the reduced diffusivity. How can that be explained?
Well, so I think I briefly mentioned that it is a combination of gradient and diffusivity. And diffusivity goes down, but the pressure goes up, flame thickness gets much narrower. So the gradient gets steeper. So the net effect turns out to be higher diffusion, which was, yeah, to me, honestly, it was rather surprising, but that's what the result is found. Maybe there's additional.
When the flame thickness is thinner, when the gradient gets steeper, does that mean the reactions get faster and therefore leading to thinner flame and hence the effect?
Yeah, which means if your reactivity enhances, you have to transport faster to burn it, right? So
yes, so the reactivity is pushing the gradient.
Yep, maybe that this is combined effect. Yes. So yeah, that's a good point. So reaction goes up with pressure. The mixing thickness gets narrower. Diffusivity goes low. So it's all you have to do the whole product of the three components, and the net result is a faster diffusion.
Thank you. It is a very interesting result, and only a detailed simulation like the one you did could have revealed this very interesting result.
Thank you very much.
We have another question from, I think, Nasrin, if I pronounce correctly. So hi, I have a question about the speed up by using machine learning. Did you use deep learning method to implement the algorithms? Where can I get any details about this?
Well, I must admit that I'm not really an expert in the actual deep learning itself. We are just users. So many of these, yeah, we do use the ANN and in actual computation. So a lot of times we can accelerate it without having to compute them individually, but by developing 0D database, we can do the ANN to compute the reactions. In fact, that is a kind of most common application of ANN in the reacting flow solution, the solver. And we also do that. But on top, as I introduced here, I think I'm more interested in doing other algorithmic speed up to further augment these power.
So we have another question. It is from Ning Guo, I think from NTNU. Thank you for the talk. Could you please comment on the research opportunities if ammonia is combusted with hydrogen, I think, or syngas, CH4?
Well, I guess it's an obvious answer, right? Everybody knows ammonia flame, the flame speed is 10 times slower than hydrocarbon. How can you burn it possibly? Well, answer is simple. We all know that. You make it faster, right? That's the answer. How do we do that? Either blend it with the faster flame fuels, such as hydrogen. So this is a subject about cracking. So you don't even have to have a separate hydrogen tank, but maybe perhaps you can do the onboard cracking. So store ammonia in your tank and then crack it a little bit to make some blend fuel, and that'll burn faster. Another important, the feasible approach in my mind is the preheating. This is more about industrial application. So mild combustion, obviously, and you mentioned that, preheating the whole thing. Then it can be flameless combustion. So that's another way to achieve it. Either way, I think the how we can prevent the enormous NOx formation out of ammonia flame is going to be the main deal maker or breaker. So I think we still have a lot of work to do.
There is a follow-up question also from Ningguo. So he was wondering if the UM-CAM GPU solver public available, like.
Well, I can't answer that. I think you probably need to contact Professor Raman about that. I don't think it's publicly available in the sense of like a download, like open form. But if you, on the collaboration basis, you may be able to get it from him.
Okay. Another question comes from Sri-chan. Sorry if I pronounced wrongly, forgive me. Could you please comment if we can mix burning ammonia flames with water to reduce NO or NOx?
Again, this good question. I believe you are not the only one thinking about it. I am also thinking about it. I think there are already more than a dozen groups in the world working on it. So experimentally, so show me, see if you can show that, you'll be famous. Well, okay. Thank you for coming, everyone. So.
Yeah, we are getting one more question, I think.
Sure.
So that is from Carol. Regarding ammonia combustion, lean and rich combustion can be represented merely by the difference in Lewis number.
Well, it is. Well, I would have to be more a little bit hesitant to say definite answer there. Again, here we intended to match. For this reason, we wanted to match the laminar flame speed and turbulence intensity and everything, and that's what we found. So you can isolate only the Lewis number effect. It is there for sure, and that's all I'm saying. And that I don't mean to say this is the only difference you can expect. But given all others the same, I think that will be what's boiled down to.
So it's just following the question there. All different overall reactions in lean and rich conditions should be considered.
Yeah, well, yeah, that's true. Yeah, I agree. So we haven't, I haven't gone into deep. As I said, it's work in progress. We need to look more deep into the chemical pathway analysis to understand it. I guess you have in-house people there who already knows far more about it than me. So I'll ask you later.
Okay, so the next question is from Zhi Chen from Peking University. Hi, Professor Yim. Thank you for the great talk. I have two questions. The first is, for the machine learning assisted CSP, was the ANN trained offline or on the fly? If the former, how generalizable is the training process and hence the ANN? The second is 100 to the third order cells per GPU number mechanism related? Is this number machine dependent?
Okay, the first question, yeah, in our present application, we did it offline. We did it in advance. It's not on the fly, but I guess on the fly is also an option eventually. If you have, I guess in situ, it's like similar to ISAT type of approach can be done, right? So, but the good thing is that if you're only doing the chemical eigenspace, you can run a whole bunch of 0D runs instead of multi-D. So it's not that computationally extensive. Second question about the GPU. Well, I guess, yeah, we were able to max depending. So you can easily fill up. Again, the algorithm, what is that? The operational intensity depends on number of cells as well as a number of species and number of reactions all together. So I guess it's a product of all. So 100 cube is not a kind of a golden rule. It depends. It depends on the what kind of mechanism you use. For example, if I'm doing the gasoline mechanism, that you can easily saturate the GPU with much fewer number of cells. In which case, you need to reduce the size of the load. So I think we should be able to come up with this total value for that. Thank you.
That's the end of this talk. And thank you everyone for coming. And thank you for the very nice talk.